Okay, we're going to now talk about rolling motion without slipping. So in this diagram, a wheel is rolling without slipping. The point P here, touching the ground, is instantaneously at rest. And the centre moves with a velocity v, forward. In this example here, we've changed the frame of reference. We're now looking at it from the frame of reference, if you like, of a bicycle rider. So now, from the point of view of the bicycle rider, C is at rest, and the point P is moving backwards instantaneously at minus v. The linear velocity of the wheel is related to its angular velocity through r omega. Let's have a look at the example. We've got a bicycle slowing down uniformly from initial velocity of 8.4 meters per second to rest over a distance of 115 meters. Each wheel and tyre has an overall diameter of 68 centimeters. First thing you should realise, we only deal with radii usually. So we're going to have to divide that by 2. So we're going to be asked to determine the angular velocity of the wheels at the initial instant, the total number of revolutions each wheel rotates in coming to rest, the angular acceleration of the wheel, and the time it took to come to a stop. So putting ourselves in the reference frame of the bike, as if we were riding the bike, we see this is now the situation. That is, the ground is going away underneath us at 8.4 meters per second. Since the tyre is in contact with the ground at any moment, then a point on the rim of the tyre, like this one touching the ground here, moves at an initial speed of 8.4 meters per second. So the initial angular velocity of the wheel is omega naught equals v naught over r. Because we already know that v naught equals omega r. All we did was transform it, which gives us 8.4 meters per second divided by 0.34 meters, 24.7 radians per second. The total number of revolutions each wheel rotates in coming to rest. So in this case, we've got 115 meters of ground passing beneath the tyre. And because the tyre is in firm contact with ground, any point on the edge of the rotating tyre must travel a total of 115 meters. Each revolution corresponds to a distance of 2 pi r. So the number of revolutions the wheel makes in coming to a stop is going to be 115 divided by 2 pi r, 115 divided by 2 pi times 0.34, which is the radius, which is 53.8 revolutions. Next thing we want to find out is the angular acceleration. We can use this equation for rotational kinematics, which looks very similar to the one that we use in linear kinematics. Remember, v squared equals v naught squared plus 2a x minus x naught, which is delta x. In this case, we've got omega squared equals omega naught squared plus 2 alpha delta theta. We can transform that. So now we basically take omega naught from both sides to get this part, divide both sides by 2 times delta theta, and we've got alpha. We now substitute in our numbers, 0, 24.7 radians per second squared divided by 2 times 2 pi, 53.8 revolutions. And that's a negative 0.902 radians per second squared. It's negative because we're slowing down in this particular case. Not going backwards, we're just slowing down. So this thing here, 2 pi times 53.8, gives us the number of radians, because each revolution corresponds to 2 pi radians. We could have also done it by taking the total angle through this. Theta equals L over R, 115 metres divided by 0.34 metres, 338 radians. We can solve for t the same way, just by transforming that equation. We've got t equals omega minus omega naught divided by alpha, which comes out at 27.4 seconds.